Hello, how are you doing? It's Mike again. In this video, we're going to talk about more trig identities. And I know it's a shock to most of you that there could be more, but there are plenty of trig identities. In some of my other videos, people have asked why I don't use more color. So I guess I'm going to switch it up from my normal black and white to maybe adding a little bit more color to make it more visually appealing. Some of these videos more visually appearing. So in our prior video, for the part one portion of this, we talked about our Pythagorean identities, sine squareds and cosine squareds and tangents and secants, and how they all relate. We talked about our angle addition and subtraction formulas. And now we're going to extrapolate into some that we're going to use more specifically towards our class. So these are not all of them. These are just going to focus on the ones we're going to use specifically in this course. So the first group I like to talk about are our double angle identities. And in this circumstance, actually, I sort of find it funny about how they're named such a way. I read left to right. Most people do. And for some reason, this is sort of counterintuitive to me, so I just sort of have to remember the way it's written. So most times you'll see this in textbook. For example, we'll relate the value of 2 theta, and you have to assume there's an angle theta that exists and that it's positive. And for us, we'll safely assume, we'll say, well, it doesn't have to be positive, but we'll safely assume that it is. Here we can say cosine of 2 theta. We can actually reduce this by half if I read it left to right, which is the way a lot of textbooks write this. And we say it's equal to cosine squared of theta, and then we subtract off a value of sine squared of theta. And there are ways for us to prove this. I'm not going to go into the proofs in this video. I don't think they're as important in a calculus series. Maybe trig, you'll find that important, but however, for us, it's not that important. It is based off of the angle addition formula. So if you want to, you can work on the proof yourself. But more specifically, talk about the way to relate 2 theta and reduce it to a value of theta, reduce it to a value of half. So for me, because I read left to right, it's called double angle. I think I'm going to double the angle. So I often like to see this written as the alternative, reading cosine squared of some angle theta minus sine squared of some angle theta. It means that we can double this, and we can say this is equal to cosine, and we can double the angle of 2 thetas. So that's the way that we can use this, is we can make an angle, we can double it, or we can take a value of 2 theta and reduce it to a value of 1. And this also works, and this is going to be our first double angle formula. And we'll talk about the second one here. So I'll do the second one, actually I'll do the second one the same in orange. So the second one actually is going to be a way for us to relate the angle sine of 2 theta. So the angle sine of 2 times theta. And in this circumstance, this is equal to 2 sine of theta times cosine of theta. And those are both thetas. So here I would say this one is used quite often. I don't know why, but I think calculus textbooks love sine of 2 theta. It's just a really nice double angle identity for us to remember and work with continuously. So I have seen that one pretty often. So if you want to reduce the angle by half, you can do so by using this double angle. If you want to double the angle, you can use it the opposite way. So let's go ahead and say that I have, whoops, I went down too far. Let's go ahead and look at an example. We'll do an example in red to be more colorful. Let's say that I have an angle of sine of pi over 4. Let's say I have an angle of pi over 4. So if I think about this, if I take pi over 4 and I divide this by 2, if I divide this by a value of 2, this gives me pi's over 8. Pi's over 8. So I can say this will be equal to 2 times sine of pi over 8 times cosine of pi over 8. So we can use it in this kind of manifest. And I don't know why we'd want to reduce this to pi over 8, but maybe we would. You can also, if you're multiplying these two together, we can use that in such a fashion. So again, you can verify this on your own if you'd like to. However, they do come out to be the exact same thing. You're going to get 2 over you're going to get sine of pi over 4, which is root 2 over 2, and that will equal the exact same thing if you multiply them out. So these are something you want to keep your eye on when you look at these double angle identities. So now we're going to talk about half angle identities, which I know are used much more frequently, especially when it comes to integral calculus. So when we get to calculus that involves integration, we will see these integrals usually using quite of these few half angle, and I believe there's a hyphen here, identities. So just like it says, you can take the angle and reduce it by half, and which also means you can double it. So let's go ahead and look at this. Cosine squared of theta. This will be equal to 1 plus cosine of 2 times theta, all divided by 2. And we can talk about sine squared of theta, and this will be equal to 1 minus cosine of 2 theta, and this will be all divided by 2. So we are able to reduce the angle by a value of 2, which I think works out really, really well. So you're going to see this quite often in calculus 2, especially when you talk about how to reduce and use this thing called integration. If we have to integrate cosine squared or integrate sine squared, then this is a valiant way to do it. We can reduce the cosine, and we can get rid of this squared portion. I think the technique is really involving getting rid of this square and making it just a cosine, getting rid of this square here and making this a cosine as well. So that helps us get rid of those square terms to make the integration a little bit easier. So how can we do so? So if we said, for example, we wanted to reduce cosine squared of pi over 4. Cosine squared of pi over 4. So everywhere we see that angle pi over 4, we're going to plug it into this formula. So here we have a theta. We would plug it in here. So this will equal to 1 plus cosine of 2 times pi over 4, all divided by a value of 2, and this will give us 1 half plus cosine of pi over 2, all divided by 2. And this gives us still a value of 1 half plus, okay, hopefully we're thinking, okay, cosine of pi over 2. You say, okay, that's not really, really easy for us to see, but that's okay. How can we evaluate cosine of pi over 2? Quickly draw your cosine graph if you don't have it memorized, and recognize that this is the cosine curve, this is 2 pi, this is a value of pi, and halfway, oh, look at that, is pi over 2. Halfway is pi over 2, so cosine of pi over 2 is equal to a value of 0. 1 half plus 0 gives you a value of 1 half. Okay, let's see if that's true. Let's think, what is cosine of pi over 4? And remember, this is going to be a value that is squared. Hopefully, okay, cosine of pi over 4, that's one of his favorites. That's going to be equal to square root of 2 all over 2, but we still have to square this, and this gives us a value of 2 all over 4, which equals to 1 half, and we notice we get the exact same thing. So we are safe. We are safe there to assume that these two are correct, and I won't tell you anything that's wrong. In a trig course, you might be asked to prove these. However, in calculus, it's very safe that we can assume these to be true. So again, there are many more, but these ones are very important, especially when you get to integration, integral calculus. So make sure to commit those to memory because you're going to use them quite often. So the last trig identity I really want to discuss in this course, and this is going to be the law. So let's use a different color here. So let's use pink. Law of cosines. The law of cosines. So what are we going to use the law of cosines? The law of cosines are important. So let's go ahead, and I'm going to draw a x-y axis, a coordinate plane here, where that's our x-axis and y-axis, or y-axis and x-axis respectively. So let's go ahead and say in orange that I will say we have a terminal ray here. This gives us an angle theta that exists there. And here, hopefully we recognize that if I draw this in, we should be able to see if this is my terminal ray, that this will form a triangle. So this will form a triangle. So that's a triangle. Hopefully my little dots can show where the largest leg is, which would be the hypotenuse in this circumstance. And in this triangle, I think by demonstration, we can see that we don't have any right angles the way this is currently drawn. So this is definitely an obtuse angle. It's greater than 90 degrees, and these are probably pretty acute. So in this circumstance, we can't really use our Pythagorean theorem. We can't use that c squared equals a squared plus b squared. So what do we do in this circumstance? Well, we remember that it is derived from there. So I'm going to go ahead and name these angles. I'm going to go ahead and name these. I'm sorry, I'm going to go ahead and name these angles. So I'm going to call this one angle A. I'm going to call this one over here angle B, and I'm going to call this one over here angle C. So if we think about this, each one of these will correspond. So I'm going to call this little leg c. So I really should make my capital letter a little bit more prevalent here. So this will be capital C. And this will correspond to, this one will correspond over here to a little leg a. And this will correspond over here to a little leg b. So each angle corresponds to a leg. So remember, we were able to determine these points. We can actually determine these points. So we can see how far these distances are. So this right here is the origin at 0, 0. Over here at point A, and again, this is for some value b, and b can be any value. We're going to assume that it's positive. So if we have a value b here, we see this is an x-intercept. So we do not travel anywhere on the y-axis. So this will be the point b, 0, which isn't so bad. So now if we look at the point over here. So notice here we have to find this coordinate point. So this over here means that we're going to start over here. We're going to go back this far and then up. So how do we name that? We're going to say this is going to be a times cosine of theta. So we say, how does that cosine of theta? It is cosine of theta because of the relationship of those angles theta. And that would make this b times sine of theta. So we have a cosine theta and b times, a times cosine, a times cosine theta. This, not b times sine of theta, a times sine of theta. That would have really made this a problem. So now since we have this, we could remember that Pythag identity, Pythag theorem is equal to c squared equals to one of the legs squared plus the other leg squared. The length of one squared plus the length of the other squared. So how do we make this relationship? How do we make this relationship here? We recognize that our value of c squared, is equal to a cosine. We have a times cosine of theta minus b, this is going to be quantity squared, plus a sine of theta, quantity squared. A sine of theta, quantity squared. And we can expand this out. And we're going to get this value of c squared equals to a squared, and this is still going to be times cosine squared of theta plus sine squared of theta. And this will be still, I should write this over here. So let me go ahead and take this value. I'm going to write it down here. And we'll have, I'll write it down here. So c squared equals to a squared times cosine of squared of theta plus sine squared of theta. And this is still going to be plus b squared. And then we still have to subtract 2 times ab cosine of theta, 2 times ab times cosine of theta. And this, we know cosine squared plus sine squared is equal to a value of 1. So c squared equals to a squared plus, we're just left with this plus b squared, and then we subtract off this 2ab cosine of theta. And this is how we determine the leg or the hypotenuse given that we have some angle theta and we have their the length of their legs a and b. And this is the law of cosines. So if we were to evaluate theta when theta equals 90 degrees or pi over 2, if we want to evaluate the special case of when theta is equal to pi over 2 radians, which is 90 degrees, let's see what happens. We have c squared equals to a squared plus b squared minus 2 times ab times cosine of pi over 2. And this again is if the special case of theta equaling to pi over 2. Remember, cosine of pi over 2 equals to 0. So this whole term goes to 0, and we are just left with the Pythagorean theorem.